It's a great honor actually to be here and speak in this conference in honor of Guy David. I admire his work very much, and actually the work of Guy that I know best is the work on the Manfort functional. And when I was invited to give a conference in here in Lumini, I thought actually I could possibly complete a theorem which would have been kind of in that direction, in which we have a system of partial differential equations, and I'm studying the singular set of this system, and I can bound actually the Hausdorff dimension of it. So it looked kind of nice, but then meanwhile time passed, and we weren't able to get the result that we wanted. So I submitted an abstract with something else. Then meanwhile, I can't quite actually get the theorem that I would like to get, but at least I have some partial results. So I will do something which I usually don't like if the speakers are doing, so I will not completely change the subject of the talk. Like I will still talk about the things that are promised in the abstract, but I will also add some other things in the direction that was actually the one I wanted to talk about at the beginning. But they are kind of connected, so it will not be a completely disjointed seminar. So at least I hope it's going to be acceptable. Very good. So let us start from the Navier-Stokes equations, which I will consider in three space dimensions. Okay, so this is a famous system of equations, but let me write it for you here. So V is the velocity of an incompressible fluid, and P is the hydrodynamic pressure. V is a vector field which is assumed to be incompressible. And this is the evolution equation for V. So now this term over here, V dot grad V, in components, or more explicitly, is simply the following. So it's the sum over J of Vj djV. And of course, you notice immediately that if V is divergence free, and if I have a regular solution, I can actually write this in the following way. Okay, and I like to write this term as the divergence of a matrix. It's actually the divergence of the matrix V tensor V. And for classical solution, this is an equivalence. For non-classical solutions, it's not so clear. I mean, for weak solutions, it is not completely clear. But anyway, so let me write this nonlinearity, which is the only nonlinearity in the equation, in that form. Okay, so let me also do another trivial computation, another calculus computation, which is behind, however, most of the, I mean, not behind maybe most of the results, but certainly behind a lot of results. And so if you scalar multiply the first equation by V, you actually derive the following identities. So you scalar multiply V, and then you get the time derivative of modulus of V squared. You scalar multiply this over here, you see that you have djV scalar V, so this is dj of modulus of V squared divided by 2, but then you can put the dj out, right? So you have a term which looks like divergence of V times the modulus of V squared divided by 2. Okay, then of course, if I multiply by V again, the pressure, and V is divergence free, I can write the gradient of P times V as the divergence of Vp. And then I have that quantity over there, the Laplacian of V. And it's a very well-known identity, very easy to derive, that the scalar product of Laplacian of V with V itself is actually the following quantities. The Laplacian of modulus of V squared divided by 2 minus the derivative of V Hilbert-Schmidt norm squared. Okay, so this, of course, if you're smooth enough, it's a very simple identity. And now, if you are, say, on the periodic torus or in three space dimension, and you assume that your solution is decaying sufficiently fast, you can actually integrate this identity in space, and you derive the total energy balance. I mean, the time derivative of the kinetic energy, which would be the following quantity, is actually equal to the dissipation, which is induced by the Laplace term. Okay, so this if you're smooth. Now, in this talk, actually, I'm not going to consider the Navier-Stokes equations, but I'm going to consider a perturbation of the Navier-Stokes equations, or a modification if you want. So I will replace the classical Laplacian with the fractional Laplacian. So let me not do the history of the model, but it's something which existed in the literature since long. I think the first one to propose it was Jacques-Louis Lyons. And so now, if alpha is equal to 1, we have the classical Navier-Stokes equations, but what we are interested in is a range of exponents for which alpha might be bigger or alpha might actually be smaller. Presumably, if you let alpha going to 0, so this guy is going to disappear, and then you end up with the incompressible Euler equations. Okay, now you see that this identity that I've written here, if you have the fractional Laplacian, is going to be questionable. So certainly it's not a computation which you can carry on in this way. But this identity over here, you can actually carry on, because if you think about the left-hand side, then what you have to discuss on the right-hand side is the integral of the fractional Laplacian of v times v. And then you can pass in Fourier, and you have a similar expression over here. So the expression that you have over there, if you have the fractional Laplacian, is simply the following. Okay, so now let me focus on the so-called Cauchy problem, in which you assume that you're given a certain initial data at time 0, and let me give you a table of possible concept of solutions that you can write down for them. Okay, so the weakest notion of solution that you can write down is simply a solution v, which is square summable, for which you can actually multiply v with itself. So you can define v tensor v. And then you have all the derivatives understood in the sense of distributions. So distributional solutions require v, which is in L2 of time and space. If in addition you require that at every time slice the total kinetic energy is finite, so that that it is L infinity in time with values in L2 in space, then you are in the energy space. Okay, so probably the best known notion of weak solution is, however, the so-called Leray-Hopf weak solution. So in his fundamental paper in the 30s, Leray was able to prove not only that there are weak solutions for every initial data v which is in L2, but the deus ex machina of his proof is a suitable modification of this identity over here. I mean, through a suitable approximation procedure, which is actually what then finally gives you the compactness to pass into the limit and prove that the solution exists. There is essentially that this should hold as an inequality in the distributional sense. Let me not be too precise over here. So Leray-Hopf is a distributional solution plus the energy inequality in the global sense. And actually, I don't know. Honestly, I didn't look carefully into the literature who was the first one to remark this. But it's pretty easy to see that the proof of Leray, which is valid for the Navier-Stokes equation, so for alpha equal 1, can be easily extended to all possible range of exponents alpha. So you can simply take Leray's proof and transfer it to any fractional Laplacian, and you will prove that for any initial data v in L2, there is actually a distributional solution which satisfies also the global energy inequality. Okay, so the existence can be done for all alpha without any problem. And then 3, there is a concept of solution which is called suitable weak solution. So these were introduced by Scheffer, I think. And I'm not sure whether Scheffer in his paper simply assumed they exist or if he gives an argument for the existence, but certainly Caffarelli con Nirenberg, slightly later, they give an argument about the existence of these solutions. And actually, it's not too difficult to see that if you look again at Leray's paper, you realize that he's producing suitable weak solutions, in fact, already with his original argument. So, and these are solutions in which not only you have the Leray-Hopf, but you have this identity with an inequality. Okay, so of course, this makes perfectly good sense for alpha equal 1. So here you have this additional inequality. It's not so clear what should replace actually this for the fractional Laplacian. But it is possible actually to do it even for the fractional Laplacian. And it has been done by Tang and Yu in the range of exponent 3/4 less than alpha less than 1. And the subject of, part of the subject of this talk is that it's possible to write it also for the hyper-dissipative case, and this is a joint work with Maria Colombo and Luigi De Rosa. And this will be the part of the talk that I actually had hoped of having finished by now. So at least this part, the fact that there is a suitable notion of weak solution in which you have to replace this right-hand side with something else, this is certainly correct. So this we can prove. Okay, so this I don't remember, but it's not very long ago. Okay, and then of course there are classical solutions. And classical solutions just mean strong, they are smooth, they are regular enough, and you can carry on all the computations that you want. And what happens for classical solutions? Well, of course, we know that there is the celebrated blow-up problem for the Navier-Stokes equations, and there is the same problem until actually alpha hits a certain critical threshold. Okay, so up to alpha less than 5/4, this is open. And then from alpha bigger or equal than 5/4, then you have actually the existence of strong solutions for all times. And in fact, you can do slightly better. So you can improve this alpha equal to 5/4 logarithmic in a logarithmic way. And this is due to tau. And in fact, there is an even sharper improvement in which you have some kind of Dini type condition for how much you can go down from the 5/4. And this is due to, I think, Barbato, Morandin, and Romito. Okay, so now, where did I put it? So I had to, over there. Okay, so let me see if I said everything, all that I wanted to say. Yes, okay, so now finally I can actually tell you. So the first theorem is what I announced in the abstract. Okay, so no, wait, I'm actually mixing up, sorry. I'm mixing up the people with which I'm working. So sorry, so this one, I guess Luigi is probably complaining already. Okay, so this one is actually Colombo and Annalisa Massaccesi. Sorry for that. Okay, and this one actually is the theorem with Maria and Luigi. Okay, so now it's correct. Okay, so what can we prove? We can actually prove that the Leray-Hopf weak solutions are non-unique if alpha is small enough. So if alpha is less than 1/5, the Leray-Hopf weak solutions are not unique. So there are initial data for which you can produce infinitely many solutions starting from this initial data and which satisfy this energy inequality above. And in fact, so this uses methods which I have introduced with Laszlo Székelyhidi. And actually, what we suspect is that it should be possible to improve this theorem to alpha less than 1/3. And this is what Luigi is working on. And this is related to something which is called Donsager's conjecture, which has been solved using, in part, the methods that I have introduced with Laszlo by Phil Ez only recently. Okay, and actually, if you don't care about Leray-Hopf weak solution, it's not difficult to see that these methods gives you non-uniqueness of distributional solutions as long as alpha is less than 1/2. But okay, actually, this theorem has become obsolete a couple of days ago because Tristan Buchmaster and Vlad Vikol have actually been able to prove, again in the framework of what I have introduced some time ago with Laszlo, so in what is called convex integration methods for these type of equations, but with very important and substantial new ideas, they have been able actually to prove that weak solutions of the Navier-Stokes equations are not unique. So the weakest notion of solution without the Leray-Hopf. And this has been just put on the web. So Bookmaster, Vikol. So weak solutions of the classical Navier-Stokes equations are not unique in the energy space. Yes, number one type solution. Of course, you could ask whether, I mean, for the moment, in their paper, they're pretty far from getting Leray-Hopf. That's, of course, what they're shooting at. And it must be mentioned that actually it's already 5 or 6 years that Schwerak, in a joint work with Gia, conjectures that the Leray-Hopf weak solutions are not unique. I mean, certainly a question that would arise is how far you are then from the millennium problem, right? So because we know that if we start from a smooth initial data, as long as the smooth solution exists, it has coincide with the Leray-Hopf weak solution, okay? So now beware here, you're always starting from a rather irregular initial data, right? So you cannot apply weak strong uniqueness because in these constructions and also in the conjecture by Gia and Schwerak, if there is a bifurcation, it's just from time 0. I mean, the solution is already so singular that it's allowing you to have a bifurcation. Okay? Very good. So, but this was not the part which I intended to present here at the beginning. So what I actually thought I could complete, so one of the things that I'm not completely happy is that when I go around speaking about these things, I always come out as being the person who proves that solutions are unreasonable. But I actually like to prove regularity theories a lot of times. I mean, at least when it's possible. So, there is, of course, the classical theorem by Caffarelli con Nirenberg about suitable weak solutions. And the theorem by Caffarelli con Nirenberg says that if you take a suitable weak solution of the Navier-Stokes equation, then it might be irregular, but the set of points in space-time where you might have irregularities is a closed set which is rather small. In particular, is less than a curve, at least. Okay, so the theorem says, so let me give you actually the kind of most precise statement possible. So let Vp be a suitable weak solution and introduce the following notation. So this is a notation which is very common in the literature. So these are the so-called parabolic cylinders. So they are the cylinders which scale naturally with respect to the it equation. So it's a ball of radius r in space centered at a point x multiplied by an interval of time of size r squared, right? So here you see the parabolic scaling. Okay? So assume you have a Leray weak solution, a suitable weak solution, and assume you have this notation. So then there exists here an epsilon 0 bigger than 0, which is an absolute constant. Oops. Okay, this one I want up. And I want this one up as well. So, and probably since the first one is shadowing it, maybe the best is to do this. Yeah. Okay, so if you have a point where the lim sup as r goes to 0 of 1 over r integral over the cylinder of dv squared is less than epsilon 0, if you have this property, then xt is a regular point. Okay, notice that it's not exactly the type of epsilon regularity theorems that would make a person in regularity theory happy. So the usual theorem which makes you happy is something like, at scale r, some quantity is below a certain threshold. At scale r over 2, you're smooth. You don't know here when you will be smooth. It's maybe at a much, much smaller scale. And you have to assume that through all the scales, this guy is under control. Okay? Nonetheless, it's a very simple covering argument after you have this to kind of count the number of cylinders where you could actually fail this condition. And you see, since I have a control on this guy, which is the total integral of the derivative of v squared for the classical Navier-Stokes, this can possibly fail only on a set of dimension 1. And actually, you can do slightly better. So the measure, the one-dimensional measure of the singular set has to be equal to 0. And since you're actually using parabolic cylinders, you can introduce an appropriate notion of parabolic Hausdorff measure and prove that you're equal to 0 over there. In particular, it's interesting because the parabolic Hausdorff measure projects on time into the Hausdorff 1/2 dimensional measure. Okay, so hence, the parabolic one measure of the singular set of U, actually it's called V, so the points for which there is no neighborhood in which V is smooth, this is equal to 0. Okay, so this is the celebrated Caffarelli-Condorcet result. Okay, so now for the, I shouldn't cancel this, right? Okay. So for the hyper-dissipative case, no, this doesn't work. I'm not tall enough. Yes. So for alpha between 1 and 5 over 4, well, probably I have to exclude 5 over 4 to get, because in 5 over 4 we know the solutions are smooth. Okay, so for alpha between 1 and 5 over 4, so there was in 2002 a very interesting paper by Katz and Pavlovich in which they proved what they call, they themselves call this a cheap Caffarelli-Condorcet inequality. So it's not my language. So cheap Caffarelli-Condorcet inequality. I don't even agree. It doesn't look that cheap to me. But anyway, so the theorem says that if V0 is smooth enough, this is just technical. So the initial data has to be smooth enough. And V is a smooth, again enough, solution of the Navier-Stokes equation with fractional Laplacian equal to alpha. So let me call it NS alpha. At the first blow-up time, if it exists. Of course, if it exists. the set of singularities, so the set of singular points in space, has dimension, so has Hausdorff dimension less or equal than 5 minus 4 alpha. Okay, and it doesn't tell you that actually they have measure 0. So from the proof, it could be in principle of infinite measure, if I'm not mistaken. So you see this is 5 minus 4 alpha matches the Caffarelli-Nirenberg result, because if alpha is equal to 1, then you get 1 over here, right? And it matches, of course, the smoothness for alpha equal 5 over 4, because then you would have simply 0. Okay, so it's compatible. But of course, once you look at this theorem, you could raise the natural question of whether you can, in fact, embed this cheap Caffarelli-Nirenberg inequality into a kind of strong Caffarelli-Nirenberg inequality. If you can actually come up with a notion of suitable weak solution for which you can prove the same result as Caffarelli-Nirenberg. So probably the best result that you can aim for is that the parabolic 5 minus 4 alpha measure of the singular set in space and time is equal to 0, okay? And then that theorem would just be a corollary at the first blow-up time. And actually, it would be also a slightly stronger statement, because you would be able to prove that the Hausdorff measure, the Hausdorff 5 minus 4 alpha dimensional measure at that time is equal to 0. Okay, so initially what I had planned for this conference is to tell you that, yeah, I can do actually the non-cheap, I mean the expensive Caffarelli-Nirenberg inequality, but not yet. So this I should probably not do it, but I think optimistically maybe in 2018 we get it. So, I mean, we have preliminary computations which look very optimistic. So I can't quite prove that, but at least I can do a first step towards it. So first of all, what we can do, so this is Colombo, myself, and Massacesi. So there exists a suitable notion of suitable weak solution. Okay, so that's 1. 2, I cannot prove the epsilon. I mean, ideally what you would like to prove is something like if the corresponding thing over here with, say, the corresponding fractional Laplacian thing has the same. I mean, here there will be, of course, a scaling factor. The cylinder would scale in a certain way because it's now not the Laplacian, but the alpha Laplacian. So here you would have to the alpha. But the idea would be if the lim sup of the appropriate quantity is under control, then you're regular. Maybe you have to throw in some additional assumptions because there might be no local disturbances to this, but morally it should be something like that. Then actually that point is a regular point. And of course, out of a covering argument from the usual bound on the energy, then you would actually derive the conclusion that you want, right? So I'm not able to do that, but we are able to do a Scheffer type regularity result. So a Scheffer's type epsilon regularity theorem. So this is really something that we can prove. So it's not on the web, but at least we have a complete proof written down, even in LaTeX. Okay, so what was actually Scheffer's initial epsilon regularity theory? So Caffarelli-Nirenberg picked up a program which was initiated by Scheffer some 5 or 6 years before, in which he was looking at these suitable weak solutions, and he was trying to prove partial regularity results. So the Caffarelli-Nirenberg is a refinement of a first estimate by Scheffer. The first estimate by Scheffer had, instead of the exponent 1 over here, it had 5 over 3, okay? And how actually did he prove that? He had an epsilon regularity theorem in the classical sense. So this is essentially Scheffer, I think, 77, maybe 78. So, and his theorem was if at a certain scale, the integral of modulus of v to the power 3 plus modulus of p to the power 3 halves. But now this scales differently, so here there is 1 over r squared. If this guy is less than a certain epsilon 1, so here there exists an epsilon 1 bigger than 0, if that happens, then V is smooth in the cylinder of radius r half. So it's really an epsilon regularity the theorem like the type that you would like in geometric analysis. Your certain quantity is less than epsilon here, then in half the ball, you're actually smooth already. So you don't have to wait for a very small scale, as it happens for the Caffarelli-Con-Nirenberg. And for the suitable notion of suitable weak solution, what we can do is the following. And anyway, I mean, in some 5 minutes, I'm going to tell you what is the suitable notion of suitable weak solution. So I don't want to hide that. So then the theorem is, and this is, again, joint work with Maria Colombo and Annalisa Massacesi. And this is, of course, this year. And the theorem is that if, and now Vp solves n as alpha for alpha between 1 and 5 over 4, and on the corresponding parabolic cylinder, now here I have to get the number correctly. Yes, here it is. So, and then here there exists actually 2 constants. They are epsilon 2 bigger than 0 and eta bigger than 0. So if the integral over a parabolic cylinder but scaled with respect to the alpha Navier-Stokes, and here I have something slightly different. So I have the maximal function of v to the power 1 plus eta, and then essentially has to be something like the L3 norm, so to the power 3 to the 1 divided by 1 plus eta, plus modulus of p to the 3/2. If this guy is less than this appropriate constant, epsilon 3, then V is smooth in the cylinder of half radius. Okay, so, and you see that I have something slightly different. That is, I have a maximal function over here, but that's not a surprise. I mean, the actual theorem of Scheffer should be kind of false if you only assume something local, because the fractional Laplacian is not local. So you need some form of control, even for the scales which are far away. Okay, so there are actually, we can prove more refined versions of this theorem, but this is one cheap way which looks very similar to what I was doing before. And probably it's only technical. I mean, in the argument, it's just comfortable to not have L1 because sequences of functions bounded by in L1, they converge actually to measures, which is slightly inappropriate. So it's slightly better to have eta positive, but I think it's only a technical problem. I mean, we could probably put eta equals 0 and there's no real issue. Okay, so that's, in a sense, the theorem of Caffarelli-Con-Nirenberg is a refinement, but it's not only a refinement. I mean, that theorem of Scheffer is a step to prove this. So what we hope is that that theorem over there is a step to prove what is the proper generalization to suitable weak solutions of the Katz and Pavlovich theorem. And I mean, hopefully we can complete this soon. So we just have some preliminary works on this. Okay, so let me tell you in the next, I think I started 3 minutes later. Is that correct? So I have until 12:03. I mean, I'm Swiss, so pretty precise.
3 equals 2 in this lemma. Epsilon 2 equals epsilon 3.
Oh, yeah, absolutely. Thanks. Yep. And maybe the statement should be for every eta bigger than 0, there is an epsilon 2 such that it's doing this trick. And eta does not have to be too large. I mean, less than 1, say. Okay, so first of all, I told you actually that Tang and you have already introduced a notion of a suitable weak solution for alpha less than 1. And you see you are between 3/4 and 1. Actually, this 3/4 is just because in this identity, you have to take the product of 3 copies of V. Okay, so you have to be in L3. So this 3/4 is just the borderline case in which you can actually make sense of this part. Okay, and in their paper, they have proved the equivalent of the Caffarelli-Kohn-Nirenberg result in, say, the sense of Katz and Pavlovich, proving that in the subcritical case, you have actually that the parabolic Hausdorff measure 5 minus 4 alpha of the singular set is equal to 0. So they do have actually already a notion of suitable weak solution. And let me tell you what is the idea. So the idea is that meanwhile, people worked out very nice tools to work with fractional Laplacians. In particular, Caffarelli and Silvestre introduced an extension trick to define the fractional Laplacian in a different way than using Fourier theory. So maybe it's not appropriate actually to have a talk like this here, because it's like we are trying to avoid harmonic analysis in a sense. But okay. I belong more to the people that like to integrate by parts than taking Fourier series. But okay, so Caffarelli and Silvestre noticed the following. Let me just, and this is really beautiful, so let me give you the simple case, the case in which alpha is equal to 1/2. Okay, so take a function u, for instance, in R3. Okay, so extend it harmonically to the upper half 4-dimensional space. So let us call the extension U star. Then the Dirichlet to Neumann map is the fractional Laplacian with 1/2. Okay, I guess this was probably well known. There is actually an analogous thing that you can do with any alpha between 0 and 1. Okay, there is something analogous that you can do with alpha between 0 and 1, but then it's not so nice anymore because it's solving a linear equation, but with a weight which is degenerating towards the boundary, right, of the upper half space. Okay, so let me not enter into detail, but it's possible to do it for alpha between 0 and 1. And now you see immediately what's the catch of this. So if you are trying to make sense, so in the notion of a suitable weak solution, I want to make sense of this product in a localized way, right? So if I had the classical Laplacian, I had that Laplacian of u times u is equal to Laplacian of modulus of u squared divided by 2, and then I'm subtracting du squared. Okay, now if I have something like this, I can actually write it as du star d mu at R3 times u star. Okay, so now when I'm making sense of this identity in the sense of distributions, I'm just testing with the test function. And of course, the nice thing is that once I have this writing, I can put the Laplacian on the test function. Okay, so now what happens if I multiply by a test function over here and I'm integrating in R3? Well, of course, now this becomes a boundary integral of a divergence because the Laplacian of u star is equal to 0. So this is actually the integral over R4 plus, right, of, so minus the integral of this of, so gradient u star times gradient phi, and I have the term which is plus integral of gradient u star squared times phi. So here we go. Actually, I've been able to localize, although I have had to make this extension, I've been able to localize what I was doing before in the global with Fourier. And OK, so once you can actually have this, you can introduce a suitable notion of suitable weak solution. That's not difficult. Now, what happens for alpha between 1 and 2? Well, something similar can be done. And there is a preprint of Young online. So similar for minus Laplacian alpha, minus Laplacian to the alpha in the hyper-dissipative range. And it only becomes a little bit more bothering because instead of extending it as an harmonic function, if you are in the range between 1 and 2, you actually have to extend it as a biharmonic function. So you have to use the bi-Laplacian. And in fact, if you're trying to do things for 3/2, you can extend with the bi-Laplacian. But if you have alpha which is in between, you have a more complicated linear elliptic operator of the 4th order. Okay, but you can do it. And once you can do it, you can make integration by parts, and then you can define a suitable notion of weak solution with which you can work. Okay, so I'm not going to give you the computations because after all, they are not, I mean, they're mostly tedious. So how do you then prove the Scheffer's type theorem? So in our proof, we are using Lin's idea in his paper in which he simplifies the Caffarelli-Kohn-Nirenberg. And OK, so Lin's idea looks very similar to the literature I like most, which is the literature on minimal surface equations, which after all is where I originally come from. So let me tell you Lin's idea in the case of the Navier-Stokes equations. And then let me tell you how at least you can try to modify it for the alpha Navier-Stokes equations once you have this concept of suitable weak solutions. Okay, so Lin's argument. Okay, so first of all, you're trying to prove Scheffer's theorem, and Scheffer's theorem is kind of scale invariant. So what you want to prove is that if you have a bound on your solution of this type, okay, then V is regular in the cylinder of half the size. Okay, and now you're solving the classical Navier-Stokes equation. Okay, so you argue by contradiction and say, okay, let's assume it's actually not okay. So let's assume that even if you give me epsilon very, very small, that's not going to happen. So what you're left is you're trying to study a sequence of solutions for which you have the following behavior. So this thing is actually going to 0. Okay, so now you notice something interesting, and the something interesting that you notice is that when you test your a local form of the energy identity, which is this one, with a positive test function, so you test this with phi, right, and integrate. So now you see over here something interesting is happening when you put the Laplacian on phi, you get a term which is the L2 norm of V. So here when you put the gradient on phi, you get a term which is the L3 norm of V and the product of P with V, which is under control by these guys, right? Because you have the L3 Hertz norm and the L3 norm of V. But this minus dV squared actually comes with a negative sign, so you can put it on the other side. And what you're actually gaining is that the L3 norm of V and the L3 half norm of P is controlling a higher derivative, which should hint that actually the sequence is converging nicely. So in particular, what you can actually prove is that if I call this, say, Ek, this quantity, which I don't know, I should scale appropriately. I mean, for instance, I could call Ek this quantity over here, and then I could call, say, Fk this quantity over here. You can rescale Vk and Pk so to have norm 1. And once you make the rescaling, you actually have enough compactness to say that you're converging strongly. Now, you have enough compactness to say that you are converging strongly, but the nonlinearity, thanks to the fact that the nonlinearity is a product of two things which are small. I mean, you're rescaling one of them, but the other one remains small. The nonlinearity is going to 0. And you converge actually to the linear Stokes equation. Now, the linear Stokes equation has smoothness. Particular, for instance, you have C alpha estimates. Now, of course, you want to have a contradiction. You want to say, wait a second. I mean, your VKs have to be irregular. Of course, you cannot argue directly by contradiction, but you have strong convergence. It's actually going to tell you that at least your VK in some norm has improved inside. And maybe it's an integrable improvement. I mean, maybe, for instance, some L3 norm has decayed. But what you have discovered is that if this decay is going on all scales, and then you actually need to repeat this argument on smaller scales, you actually have a decay for a certain integral. So you are in some Morrey space, and you are C alpha. So that's essentially the basic idea of Lin. And now the question is whether you can actually carry on this type of procedure even in your NS alpha situation. And the answer is that at least at the first sight it looks nice, because the basic mechanism which is behind this proof is that the quadratic nonlinearity is disappearing in the limit when you are making that type of rescaling. And of course that happens even in the NS alpha situation, because the quadratic nonlinearity is exactly the same. So there are anyway several technical problems that you have to face. So we want to repeat actually. So we want to repeat the scheme. So we want to use this scheme, which, by the way, is not the scheme that Tang and you are using for alpha less than 1. So in the NS alpha case. And we have the following problems. So first of all, the thing is non-local. So you can't possibly argue completely by only looking at what is happening in the interior. You also need to control something outside. And you end up in the limit by discussing a linear equation, which is kind of strange. I mean, it's linear in a certain domain, but outside, actually, it has some error terms. So non-locality is certainly an issue. A second issue is that actually in the hyper-dissipative case, you have bilaplacians floating around, which means that your energy inequality is actually able to control the bilaplacian, but it means it misses somehow a control of the lower order terms, that you won't interpolate between them. That creates some problem that actually can be solved by some classical tools in elliptic PDE, and which are usually called hole filling techniques. Okay, but this goes very much in the technical side, and I'm essentially over with my time. Thank you very much, and happy birthday.
Or comments?
So do you know, I mean, is this epsilon 2 really depending on alpha, or you can make it uniform if alpha?
Current proof is depending on alpha. It would be nice to have it uniform. But somehow the way we are proving things degenerates when we get to the Laplacian. And I'm not yet sure how to do that. I mean, to tell you honestly, we are also focused on getting the full Caffarelli-Con-Nirenberg, so we didn't spend much time in looking on how well you can actually do that proof. I mean, for the moment, we just have the first proof that works, and probably it's pretty sloppy.
Other question? If no, we thank Camillo again.